So hi, I'm Pierre, and I'm a senior data scientist at DataiKu. And today I'm going to talk about Medicare fraud detection. Wait, all right. Okay. So it's supposed to be hands-on, but if you don't have a computer, or if I go too fast for you, or if we just don't have time to finish everything, I put all the material online, so you can actually download the data and all the scripts I use, either Python or the SQL stuff. Sorry for the R coders. I have my package R I designed back in the days, but I haven't been using it for like 1 or 2 years. So now I do only Python. Okay, I just want to know, we've kind of did background check, but how many of you are familiar with like the basic concept of machine learning? If I tell random forest, it's okay for everybody? Yeah. How many of you know SQL? And how many of you do like window function in SQL? Like what? Okay, so yeah, window function is basically if you do, for example, select star, comma, rank over partition by something, right? Yeah. It's like when you use the over part in the SQL stuff. Okay. Right. So it's pretty common, but it's very used, and we're gonna do a lot of it today. So how many of you do know Python? Okay, and if I say pandas and Scikitlearn?
What? Sorry.
Pandas and Scikitlearn. There are two very well spread packages for Python. Scikitlearn. Over there. Scikitlearn. Pandas is for reshaping data, mostly, and Scikitlearn is for the machine learning part. And how many of you know Kaggle?
I know what it is.
And how many of you did enter a competition? So, what's the score? Best score?
This was way back. I was in the Titanic.
No, real one, not the Titanic.
No, that's the only one that I tried.
Anyone with like a 25 or 10%?
Yeah.
10%.
Yeah.
10%.
Good. Good. Which one? Which one? Ah, yeah. Yeah. Cool.
Our bootcamp just finished the coupon competition. They're top 10 now.
Coupon, the coupon is just new, no?
Yeah, it's not finished yet.
Ah.
It has 2 more months.
Yeah. It's not an easy one, this one. It's,
Yeah,
you got to do last stratified stuff. Probably. I did not try this one. I'm on 4 others right now, so I don't have time to try everything.
We're also going to teach it in the bootcamp. How to
Okay.
do the coupon competition.
Cool. So who I am, yeah, but, well, I said everything. You can check my Twitter account if you want to have the thing I publish on data science. So quickly, introduction, what we're going to do today is I'm going to show you on the slides what's the Medicare data and what kind of database you have and what you can imagine with that. And then after that, we're going to have a end-on session where we'll talk about feature engineering, which I did in SQL, and machine learning models, which I did in Python. So the goal is to iterate, like you have your first bunch of features, you try some machine learning, like logistic regression, and then you say, okay, I need more information, so I add new columns on my training set, right? So this part is not very interesting today because there are very few lines in the supervising we're going to do. So the part here is not very stable. The interesting part is more the feature engineering stuff and how to design that with SQL. So all the material is available here. I also posted it on the Meetup page, so you have a link. And if you don't have downloaded every data, I should have a key or drive with the data. So for users who want it.
Yeah, I noticed like one of the files was over an hour to download.
Yeah, it's 1.3 gigabytes. It's the SQL dump.
Yeah.
So if someone wants the data, it's over there. All right. So Medicare data, what do you have on the web? Most of it is open data, and there are a lot of different websites with this kind of information. But the first one to check is data.medicare.gov. You have very basic information. You have the physician information first with NPI, which is the identifier, which is the used. So that's what I use to do most of the joins between data sets. And then you have a lot of information like the specialty, the name, last name, address, like really a lot of information about the physicians. You also have the same kind of information about hospitals, nursing, dialysis facility, and so on, but it's mostly static. Then, so this is an example of dataset you can have. So you have this NPI, and then you have the last name and the first name of the person. You have his gender. You also have the medical school where he learned his medical thing, when he graduated, what's his specialty. You have like 5 fields after that about his specialty, where he works now, everything. You have really a lot of information. You can probably geolocate everything because you have addresses, not that many codes to do on a Google API, so it's possible. Then you have the CMS data, which is probably the most well-known, and you have several data sets with different level of aggregation.
Yeah, I only need to copy Medicaid fraud detection folder, right? Because you have a lot on that thing.
The other thing is mine. Like
Those
perso
two
means
folders?
mine in French. So just the Medicare stuff.
Okay, great.
The other stuff is mine. It's personal.
I'm sorry, I don't know.
No problem. So the most well-known is Part D, where you basically have all prescription from a physician aggregated on the level of the physician and the drug and the year. So, for example, if you look at Part D, if you look at the data, it looks like this. So you have this NPI, you have the drug name, and you have the total claim count, which is the number of prescription you did, the total day of this prescription, and total cost for Medicare. If you want to have more data, because in CMS you probably can find only 2013, I guess, you have ProPublica that has other data sets. And for example, it has Part D 2011 and 2012, which we're going to use. And they also have a lot of different data sets where they have cleaned and merged stuff to make it more understandable for people. But these are mostly not free, and you can actually do it by yourself most of the time. Then you have also this data set, which is basically the payments. So for every physician in the US, you have to declare if a pharmaceutical company gives you money for whatever reason. So in this data set, you will have, again, a profile ID, but not NPI. So it's not easily joinable. We will have to use first name and last name to join with NPI. And then you have the name of the company and the total amount and a lot of other information about why and how they did this payment and date and so on. And I found this dataset, which is an exclusion dataset. So tonight it will be the proxy for fraud, which is still a proxy because, as you can see, there is sometimes a rain date, which is actually, it was excluded, but it was cleared. We're not going to use that, so the target is messy, right? And also, it does not detect every fraud because for example, there are examples where someone was not a frauder, but all the prescriptions were made in his name. So in our data set, it can be detected as a fraud, but in the target, it will still be 0 and not 1, because the guy was not excluded, because he wasn't a frauder, right?
Can you repeat that again?
Sorry?
Can you repeat that again?
Here?
Yeah, the one about the fraud.
Yeah. So I don't remember the name, but if you look at ProPublica website, there is an example where there is one physician, and they detect that there must be something which is weird, because from 1 year to another one, he asked like Medicare for $1,000 and then several millions. So something was weird. But the guy was not a frauder. Some other people were using his name for the prescriptions. So as a result, if we look at our data sets, the features how we design them, probably we will find that this guy is a frauder, right? The problem is that in the targets, it will not be, because he was not excluded from the list, because he is not a frauder. Other guy used his name. So that's why our target is not very good. And I mean, like, what we're gonna talk about today is not about real detection and something like this. I'm not a Medicare expert. What I design is more a toy than something that can actually be used. I mean, with some guy actually from Medicare or the police or whatever, if you tune well your target, then you can actually do something. But you prefer to use a target which is not perfect, also because I don't want to have a good model and say, well, actually my model says that this guy is a frauder. I don't want people to ask me this kind of stuff. So let's say our target is pretty messy, but it's a proxy, right? And so we have other data sets we will not use tonight, like the FDA data set. You have a data set of drug approval. What the interesting thing is that you can have, for every application, you have the drug name, and you can correlate this with active ingredients and molecules and so on. So from one brand or one drug name, like, I don't know, aspirin, you can actually have the molecule behind that and do analysis on molecules, active ingredients, and not only the brand. So if you do some fuzzy join on the drug name, then you can group by active ingredients, and probably the active ingredient is what you could say a generic name. So from that you can compare for example, every company compared to a same medicine drug, right? Also, there is Eric's known datasets where you can have like way more scientist stuff about the molecule and so on. So you can, this is harder to use, but it's very interesting. Lots of information there. So conclusion, you really can do a lot of stuff with these datasets. If you want to have more ideas about what people do, there is this very good website which is ProPublica, where they basically do some data journalism about Medicare data. So you can find a lot of stuff there. They also have some thing you can check and just play around to like have a look at the physician in your neighborhood if they have too many payments from companies. So you can actually have a look at if you go to your physician and he prescribes some brand name drug, you can have a look at if this guy was paid a lot by this same brand on the past year. Also, there was a very nice page rank for anomaly detection. I'll share you the slides later. So today, what we're going to do, we're going to try to create a fraud and abuse detection system. So according to ProPublica, it costs around 2.2 billion per year. And the question is, can we design a tool to help detecting fraud? So the idea is not to create some automatic detection, but more to create a score that will help people check on physician. So for example, if I give you probabilities that it's fraud and you follow everything given the probability I gave you, if my model is good, it's still better than looking at random, right? It's a good idea to actually use this score. So for example, my final model, if you take 10% of the physician, you retrieve 62% of the frauders, which is way better than random, which would be 10%. Okay, so tonight we're going to talk about three stuff. So first, supervised learning. So the problem is basically a two-class classification, one for frauders and zero for not fraudsters. The target is exclusions. Like I said before, it's not a good target. And we're going to have the AUC as performance metric, just because in these kind of problems where you actually have people you have to have people to have a look at things. You probably can only look like, for example, 10 physicians a day or whatever. So what's important is not the accuracy or the recall or whatever. It's the 10 first person. So the important thing is the order. And AUC measures that. That's why you use AUC for
What is AUC?
AUC is the area and the ROC curve. Like
Area, what kind of curve?
ROC.
ROC?
Yeah,
Okay,
ROC.
good.
So one way to interpret the AUC is that it's the probability that your model differentiates correctly between a true positive and a true negative. So that's the probability that you have the correct classification.
Yeah. But yeah, the main idea why I use the AUC in this kind of stuff is because of the order idea. Because, for example, if you use F1 score, it's not really optimizing F1 score here. It makes no sense to my mind, I guess. So we're going to talk also about feature engineering. So everything we're going to do in SQL. So first, basic sum and counts.
I have a question.
Yeah.
The exclusion data set has been produced manually by experts?
Yes, I think so.
Okay.
You can
It's
find
based
it.
on human experience.
Yes, it's the real excluded person for fraud. So it's on a fraud website with the American Eagle and so on. But you can have a look at the data. I post the links. So then we're gonna do some very basic outlier features. And then we're gonna have fun with graphs because graph is fun for fraud. And then we will incorporate payments. And then if you have IDs, we can try that. So this is for later. All right. So we're gonna go to the project. For those of you who have the data and want to follow, I'm gonna start showing things on SQL. Right. So this is the product my company designed. I'm not gonna talk about it because I just want to talk about the SQL stuff.
Okay.
The idea is that it's a data flow, and these red things are the SQL ports, and these blue things are the datasets. I'm using Vertica because it's kind of fast. So, for those of you who are following me, you have three datasets called Port D. What we're going to do first is concatenate everything and aggregate everything because we can actually design some features about 2011, 12, and 13. But today I just choose to concatenate everything.
Can you make that larger?
Yes. Is that okay? Can you read?
Thank you.
Can you read? Yeah. Okay. So this is a simple concatenation in SQL. So the only thing to be careful about is, of course, as some datasets are from ProPublica and the other one are from CMS. It's not the same format, not the same column names. So there is just a bit of change here and here. We only keep the NPI, which is the ID. The number of prescription, number of days, cost, drug name, and at the year. So this gives us our new data, which basically looks like this. All right, so you have this NPI, number of prescription, number of days, and so on, and the specialty of the person. So now we want to do basic aggregation to start creating our new features. So what we want to do is for each NPI, add some information about it. So what we could think of as the first ID would be, well, probably that a fraudster would make Medicare pay way more than someone who's not a fraudster, right? Or at least, if you see like the opposite way, someone who doesn't make Medicare pay a lot, is probably not a fraudster, because if he is, he's like not making a lot of money, so probably not worth the risk, right? So the first aggregation you can do to create these basic features is very simple, and like it's probably the SQL 101. So you just have to select the NPI, group by this NPI, and calculate basic stuff, which is so you keep the specialty, and it's the same for every line. You can take the mean or max or whatever, and then you can take the total number of different prescription. Maybe if someone does like every kind of prescription, probably weird. And then you can take the sum maximum variance of these three quantities we talked about, which are number of prescription, number of day, and total cost.
Does any of your tables have like their number of employees? The doctors often have people who can prescribe under them, but they can show up looking like their prescription, like nurses' aid,
yes, no,
and doctor assistants.
I don't have this information. It's probably available somewhere.
Oh, okay, because that could make a big difference from one year to another if they hire a lot of people who can make prescriptions who aren't them.
Yeah, you would like divide by the number of employees.
Right.
Yeah. No, I don't have this information.
Have you ever mapped this back to the IMS data of doctors' actual scripting, TRXs and RXs? Do you have the IMS data set?
No.
Okay.
No, I don't know about
You might want
this.
to check that out.
Okay.
Because that will actually give you the actual scripts that come through. Because some scripts are made and people don't actually script them when they get switched to generics.
Okay.
So the IMS data set would have all of that.
But this is about Medicare payments, so it's not about just prescriptions.
But you might want it's just like a quality control to see if it's scripting high or low. You don't want to get any, but if you want to see if it.
There are some like wrong data.
Exactly.
Yeah.
Yeah.
Sure. Yeah. Okay. So now we can switch back to switch to Python. So I'm gonna open a very simple IPython notebook. The Wi-Fi connection is not very good. All right. Okay, so in the IPython notebook, also on the website, you can download. I did a small recap of every dataset you can download and use. I did a quick recap about how you can use the data into PostgreSQL. So you have the dump. You can download the dump. So you can synchronize that. And after that, either you can use any tool you want for PostgreSQL, but you can also use an IPython notebook with a PyCopy-G2 package and actually call SQL from Python, if you prefer having this kind of notebook. So on this one, I'm connected to my Vertica database, and I read that into Python. So what I basically do is I use the read frame thing from pandas so that I transform my SQL datasets into a pandas one in Python, right? And then we can do a basic analysis. So here, if I take only the base features, I'm not sure my notebook is still loaded. No, it's not. All right. Okay. Right. So what I'm doing is just classic machine learning stuff. So I separate a train set and a validation set. The idea is that you train your model on the train and then predict on the valid and check if your model is good or not, right?
Yeah.
So most of this stuff is done with Scikitlearn. If you don't know Scikitlearn and you want to start in machine learning, probably it's one of the best packages to try. Their documentation is awesome. You basically have a free machine learning course just by reading their documentation. It's really like one of the best I ever seen. Thing is, with Scikitlearn, you always have to fill the missing values because it does not understand num. Then you can rescale or not, depending on what you're going to use. So, for example, if you use logistic regression, it can be a good idea to rescale, or even to change the distribution of your variables. But you can rescale because if you don't rescale, it's harder to understand the coefficients you get out of your logistic regression. But if you're using stuff like random forest or gradient boosting tree, there is absolutely no use in rescaling, since you keep the shape of distribution you will cut at the same places. So my IPython notebook is actually not working, I guess. All right. So then you have to, if you have categories, you can use dict vectorizer class, which is basically creating what we call dummy variables. So, for example, if I add three specialties like general medicine, oncology, and cardiology, what this stuff would do is create three columns with one each time. So the first column would be like, for example, general, and every time you have an NPI with general, there would be a 1, else 0. And then with Scikit-learn, it's very easy to train your models. You just have to declare what's your classifier. So for example, my first classifier was a logistic regression. And then you just have to call the fit method and then the predict method. That's all. It's very, very easy. So Scikit-learn is very nice for this because contrary to R, you just have one thing to know is you declare your classifier or your regressor or whatever, like your PCA. And then you just have to fit, predict, or transform. So it's very, very simple API. And then you can, of course, evaluate. So if we have a look at our raw curve over there, we see that, so this is false positive rate, true positive rate. The random model would be like this, because every time can be whatever. A model which would be like this would be not normal, since if you're using the opposite of your prediction, you actually have a good model. So that makes no sense. Actually, I have one or two toy examples where you are compelled to go there. you cannot be good, but it's really toy example. Really hard in practice to be in this place. And so obviously the best model possible is to go here into the 0, 1, and then 1, 1, because it would mean that you get every true positive first, and then after that, in the order, you would have every false positive. So I'm actually not able to show you this on this IPython notebook, but basically, if I go back, in the PG dump, I created a data set which is called complete, which is a dump of my whole final training set. The other data sets are simplified one, so that you can actually work with PostgreSQL very, let's say, quickly, because the real data is way bigger than 1.3 gigabytes. So just to have an idea of the performance we could have, I probably have my performance over there. All right. So with these very basic features, if we use a simple logistic regression and a random forest with 100 trees, we got these AUC, which are around 0.7, 0.75, which is not very good. So the question is, can we do better? And can we create more intelligent features than what we did? Because basically here, with this script, SQL script, we don't have a lot of information about each of our physicians. So we've got to enrich our training set with other features. So the first thing we could think about, which would be better, is to try to detect in some way outliers, things that would not be normal. So for example, something that would not be normal if I was some psychiatric doctor and I was prescribing something for the heart or for cancer. So that's not normal. So maybe we can have a look at the distribution of prescription and compare that with people of the same specialty. So that if I'm an oncologist, I don't prescribe some weird stuff.
Can you just go over the variables that you selected and why?
I selected basically everything.
Everything, okay.
You mean in the regression, logistic regression?
Yeah, like there's something like
Selected everything. I just have 9 variables, so I don't select anything. There is actually I use a L2 penalty with 0.1 coefficient. So it kind of shrinks, but I do not create sparsity.
Okay, so is everything, there's no linearity or anything, they're all, I have to imagine why these variables.
Yeah, what I showed you is just a benchmark. I didn't fine tune on the logistic regression part. Why? Because when I do this kind of stuff, I prefer adding more features first. Just look at the benchmark, and while it still adds some performance, it's good. Then, when I have no ideas, or when I add features and it does not add anything on the performance, I start working on the model, and then selecting variables and things like this. But when I add information and my benchmark is still going up, I don't need to waste time on making a very nice machine learning model, because it's not important, because I will add some other features, and the work I just did, I got to do it again. Right? Also, in this particular case, what I forgot to say is that you've got a target which is very imbalanced. So you've got more than 1 million NPIs, physicians, but you've got only like 300 fraudsters. So it's not very stable. So you don't want to waste too much time looking at the variables. So for example, this one of the random forests, it takes maybe a quarter of an hour to train just on one fault. So if I want to do 5 fault CV, it starts to be long. Now if I want to grid search everything and like try separate model with feature selection and so on, it would cost me a lot of time. So that's why I do that at the very end. So one way to, let's say, design these outliers variables would be to group by specialty and look at the distribution. So in SQL, you can do that with the entile function. So entile basically calculates every quantile for your distribution. So if you select like the last one, what you're gonna say is, okay, I put 1 on my variable every time this guy is like the one prescribing the most for this specialty and for this drug, right? So, and then as you have like a lot of specialty, you have to aggregate again and select the sum of these. So basically you will have a variable which is the number of time the guy is an outlier for every drug. Problem is that if you use these figures, it actually does not work. It's simple to see why it should not work. Is because even if you have people prescribing a lot, it's not necessarily outlier. For example, if you have a uniform distribution and you take the guy prescribing the most, is not very far from the second one, right? So it's not very interesting. It's not a real outlier. So another way to detect outlier is to make the hypothesis, which is not true at all, that the distribution is kind of Gaussian, and then to have a look at and to make the hypothesis that an outlier is a person that prescribes more than the average prescription plus 4 times the standard error of the distribution. The question is why 4? Well, this is a parameter and this was a grid search. So if you take 3, it works well, not as good, and if you take 5, it works not as good also. So this is just a parameter and grid search. So with this definition of outlier, you can actually make something which is better, and you can have a model that goes to 0.75 approximately. No, sorry, this one. Yep. 7 for the random forest, and you gain still 0.01 for the logistical regression. Now this is pretty, I would say the idea behind using that is that if you look at how people detect fraud in general when you don't have any labels, is to do unsupervised thing. And this is basically putting back unsupervised IDs into the supervised framework. So that's the idea. And okay, so now I'm going to talk about, so every script, I do it a bit fast because we're short on time. But you can find everything on the website. And so to create more features, I have the idea, which is pretty common in fraud, to use graph and network features. So here's the idea is to propagate the fraud information. If you look at credit card frauds, for example, it's very common to see patterns like same address email. Means that every guy using this address email is a frauder because it's the same person. Same thing for IP address and so on. So what people do is you recreate the graph and put an edge with weight 1 every time 2 persons have the same email address, for example. And you recreate this graph, and from this graph you can derive a bunch of features. For example, you can derive degree of the person, which is basically the number of neighbors in the graph. But you could also derive clustering coefficient or whatever, let's say, usual graph stuff. And another idea is to look at the distribution of fraudsters around you. So, for example, if I'm connected to 3 persons with the same IP address, and they are all fraudsters, I'm probably a fraudster. So that's the idea, is to propagate the target information into the network. Well, here it's pretty, like you can probably do only one kind of network. It's physician to physician, but what could be the link? Well, the link could be something based on drugs. So people who prescribe the same kind of thing kind of belong together in the graph, right? So what you can do is, in this graph, look at people who are fraudsters and try to look at if people near you in the graph are fraudsters or not. So it's similar to impact coding. I don't know if you guys know that. Impact coding is a very simple thing, is when you have a categorical variable, instead of dummifying everything, you just create this variable which is one column, and you impact code, meaning you just put the average of targets of the category instead of the name of the category, so that it become a continuous variable. So here the idea is kind of the same, and what we want to do is give a score to every physician using the information of fraudster physician. So the idea is, if I add, so for example, when you're a fraudster in Medicare, one of the things you would like to do is, for example, prescribe something with opioid inside, because you can actually take that and sell to other people so that they use that. Or you can prescribe lidocaine, because lidocaine is a non-solvent for cocaine. So then you use this kind of drug to cut cocaine with it, and you can make money out of it by selling to drug dealers. So actually, if you look at impacted drugs, meaning the list of the drugs which are most commonly seen and prescribed by fraudster physician, lidocaine is number 1. So most of if you look at the drugs, there is information inside. So the idea is that I want to score for a physician, which would be a weighted or not percentage of the drug I prescribe if I had a score for the drug, right? So for example, if I give a high score to lidocaine and I prescribed a lot of lidocaine, then I should have a high score. Now, how would I have this drug score? Well, what I can do is propagate the information from physician into the drug. So for example, lidocaine has a high score because a lot of physicians who prescribe lidocaine are fraudsters, right? So there's a problem with this, is that if I'm a fraudster here, I impact code this into the drug, and so when I propagate again on myself, I took the information from the target and I put that into my score. So that's called leaking. It's not good, because basically I take the information I want to predict and I put that and say, well, now that I know that, I can predict your faster. So you cannot do that. But what you can do is actually calculate the score. If you calculate the score for this guy, if you set aside him for calculating the drug's score. So, for example, like this. So if I want to calculate this score for this physician, I will use every other physician but him to calculate every drug score and then propagate everything and have this physician score. This way, I don't leak. So I don't put information from this target on this line in my training set.
But you still leak if you are clustering in the fraudsters. Which probably you do.
Which?
If you have clustering among the fraudsters, you still leak because you have a correlation between the structure of
yes.
the topology of the network, and probably you do have those correlation. So I believe you are leaking.
Yeah, I am leaking if you were to. Okay, I see what you mean, and I thought about that, and it depends on how you see the question, because actually, if there is a structure in the network, and I do a separate training and test set, I put information from the test target into this stuff. Yes, true, but I don't really, if my goal is not to predict all the guys, but to give a score just for these guys to help detect fraud that is already there. Do you see the difference?
You are very close to the danger.
I'm very close,
yeah.
But I'm not sure how to evaluate this impact. But if I'm using the same trainer, same test, I'm not sure I'm leaking. Probably not that much, and if I am, I probably have a better final prediction anyway by having a model that is kind of a bit leaky, but not that much, and a model that does not use that information because this information is very important.
Yeah.
It's basically, because when I said use lidocaine, for example, it's because I saw that in the data, and I didn't know that before going into Wikipedia page. I don't get cocaine myself.
Thanks.
So yeah, there is kind of a leak if you have like a train, test, and validation. But in this case, I believe it's not that leaky.
Okay.
Very interesting question. Another one would be, now that I have this kind of scheme, can I actually calculate this easily? Not by using Python and do this graph for each person. Can I actually write it very easily? It's actually possible with SQL. If you really like windowing, it's possible, and you will have something which is which looks like this. Yeah. So this. So this one. So what we do here is, so this is basically adding the target. So I select everything from port D, which is my basic dataset. I add case when Excel date is null than 0. If I have an exclusion date, that means that there was a fraud. So I create 1. So that's all. Just adding the target. And now you can actually write what I said in SQL with only 4 lines. Well, 4 lines plus 7 lines. Because there is some linearity. So if you have a look at the graph here, the question is, if I have a score for the drug, can I calculate the score for the drug? So if I have a global score for the drug, meaning with everybody's contribution, can I calculate easily a score for the drug for everybody but one physician? And turns out because it's linear, it's very easy, and you just have to subtract the physician score. So you can actually just calculate everything with a big leap and just separate the physician contribution on each line. So if you use window function, it's kind of not that easy, but it's possible to write this kind of complex graph features using only 4 to 7 lines.
Window was a SQL function?
Window is a kind of window function. So for example, this is a window function. So in SQL, when you can use sum. So for example, I could do select star and sum. So I could do select NPI, sum of cost grouped by NPI, which would be simple aggregation and summing everything for each NPI, right? But I could do a window function which would be select everything, so basic data sets, and add me a new column which would be the sum of the physician, of the cost for the physician, but I don't want to change the data set, so you just replicate the information for the physician every time. So for example, if I had 2 physicians, one total which would be 10 and the other which would be 20, I have 2 lines, so I have physician 1, I would have 10 and 10, right? Instead of, so I just take the data set as it is and add some information.
In your select statement you're talking about?
Yeah.
And why do they call it a window function?
That's a good question, I don't know.
Yeah, that was most confusing. I understand the code better than the name window.
Yeah. So the idea is just that you can actually write very powerful stuff with these things. For example, you can recreate sessions, you can do a lot of things, really. And so with these features, you can actually have a AUC of 0.830, so which start to be kind of good for this kind of problem given the target. And we're close to the end, so I just want to say that I added one last feature. Where is it? Probably here. Yeah. I added one feature which were the payments. So what I did was just summing every payment for each NPI physician, and then adding this feature, meaning probably that if you're a fraudster and you try to make a lot of money, probably you will go and see every pharmaceutical company and ask them for money and they give you money, right? Turns out if you look at the, it actually improved the model. So there is some information in that. Funny thing is that it's probably the opposite from what I said. So, for example, if you look at the logistic regression, you have a negative coefficient on the payments. So I'm not sure I have an explanation about this. Either fraudster want to, I don't know, be discreet, or maybe the pharmaceutical companies actually have some information about the physicians. So physicians who don't look very honest, they don't give them money. That's another possibility. And probably another one would be that as I mixed every payment, there are payments for example, research. So if you have a lot of payments, it could be because you're a researcher physician. So you're probably in a very serious hospital and so on, very highly paid, and probably you don't fraud.
When you said negative payments, you mean you can actually pull up records with negative payments, or you mean just the score coefficient is negative payments?
I just said the coefficient on the payments
is negative.
Is negative.
Negative itself. Okay.
Is negative. So the higher payment you receive.
This is less. Okay. Yeah. Perfect.
Yeah. So at the end, the row curve looks like this. You can see there are very few points because I only have 50 points over there. which is not very good. But if you actually do, I did 5-fold CV for each of these models, and it gave up approximately this performance. And the final idea is that if you look at the lift chart, you can see that we are at 62% for 10% of observation. So the model is really better than random. So I would say that only using open data and so on, if you're actually working for Medicare and you are able to create a proper target, then you can actually improve the fraud detection, or at least have a decision helping tool, right? It's possible to create this stuff. So yeah, that's my conclusion. That's all. If you have any question on, if you want to do again the hands-on with every SQL and Python's code, it's available on the website. Also, I left some cards over there. So if you want to take my email address and ask me questions later, when you're like, when you have more time to digest everything, I would be happy to enter it. All right. So, do you have any questions? Yeah.
Could you explain again the impact coding? Were you trying to
The impact coding.
so you're
Okay.
looking at doctors prescribing drugs and then how
So,
drugs prescribed?
Okay, let me try another way, because it was probably not that clear. It's because I'm very used to do this kind of stuff. So if we have a look at what I call drug impacted, which is for each drug, I take the average number of physicians that are fraudster and prescribe that. So, for example, if you are the first one is lidocaine, there is 0.1% of physicians prescribing it who are fraudster, which is way more than if you look at aspirin, for example.
What is it what criteria do they use to decide that somebody who prescribes lidocaine is a fraudster? The number of prescriptions?
I have the information about fraudster, right? So if I look at the drug, I look at every person that prescribed it, and so I can take the percentage of people that were fraudster.
Yeah, but how do you decide that is a fraudster?
How do I don't decide. It's my target. It's the exclusion.
It's given. The
Yeah.
Medicare
It's
gives
supposed-
you
it's
the
supposed
four
to be given.
criteria. Right? You're not creating the four criteria.
No,
It's
Right.
I
already-
don't.
It's already given on the
I try
data
to
set.
predict it.
Out of 1 million records, there was
300
people?
300
Yeah.
were noted as being fraud.
That's
So if you
tough.
wanted to go ahead in the future and put a scoring model together, you would have the characteristics. You can take this model and score a fresh data set and see which doctors are most likely to do,
But we don't need to know what criteria Medicare
not in
uses.
this particular case. That could be a different
The
study.
target could be biased by.
Yeah, sure, of course.
Your data is all in the open data set, right?
Yeah.
It's all on the open data.
You can find everything
Okay.
online. Only thing is the target is not perfect.
So with open data, they're not going to, there's a limit because they're not going to really give you all the nuts and bolts of how they went ahead and defined a fourth person. That's proprietary. But you can take what they do know and create applications or models or test your skills to this extent.
Of course, you would never know how much your target is biased by whoever created it. Whoever decided the exclusion criteria.
And exclusion means what again? Excluded from what?
From properly prescribing. These people are excluded because they've had high rates of illegal.
Excluded from prescribing in the future?
Yeah, that's the term that you use. Yeah, or like they're fraud. They're
Lost their
doctors
license, maybe?
that had been flagged. I should say instead of exclusion, you should say I guess flagged. They're flagged for having done illegal behavior.
Is there data on how many of them end up in jail?
That might be a different open data set.
Yeah, I guess so.
Not many. They
You
usually
probably
find.
can find that actually. It's probably
It's
possible to
probably
find
is
that.
penal. They
love
could
money
probably
more.
find it on the data
Yeah.
set who went to jail for prescribing illegal scripts.
Also, one thing I didn't say is that why my target is not very good is that trying not to break the model, as I'm using port prescription from 2011 to 2013. I used only fraudster after 2014. So all the guys who were excluded in the 2013, I didn't use this information.
Right.
So it's 0 for my target, whereas it's not very good, right?
What part of Scikit was used in this demonstration?
What part of Scikitlearn?
Yeah.
Uh,
Well, that's not part of what you presented, was it?
It is on the IPython notebook, but I didn't spend too much time on it. But you can find the code on the internet if you just follow the link.
If you're starting with Saikiran, I think it comes with Anaconda with three data sets, right? Iris, numbers.
I don't know. The actual data sets.
But I think that's where you would start. Maybe you would want to start with this one. Start with.
Okay, well, I know too little about Python to ask relevant questions at this point, so forget it. Thank you.
But if you want to start with Scikitlearn, just go over their documentation because it's very, very good, really. Like I spent my first week of my data science first job just reading that. Really, it's very, very good. So I didn't finish, right? So the idea from this stuff is that we have some drugs which apparently are more used by fraudster than not, right? Why? So if we look at the list, so what I did is I sorted by the cost-weighted person fraud with the idea that if you add the information about total cost, it's better than average number of fraudster, right? Because it also incorporates the fact that fraudster will make more cost about this lidocaine stuff than non-fraudster, because they will do that again and again, right? So you can wait and probably it's better, heuristic, right? And then I just filtered by 5 minimum fraud. So this is a list, and in the list you have lidocaine, which is used to cut cocaine. You have amphetamine just over there, I think. And in these ones, you have approximately 5 to 7 opioid drugs, which you still can use to make drug and sell that as a drug dealer, right? So from this, you can imagine that there are some drugs, if you prescribe that a lot, you're more likely to be a fraudster than if you prescribe a lot of aspirin.
Yeah, I don't see any ADHD drugs. It's all like cocaine and stuff you said. I'm just not seeing
The
it.
what? Lidocaine?
No, I'm
the
sorry.
ADHD, the rest,
Ritalin.
Ritalin, yeah.
I don't see anything.
Is it-
Adderall.
Is this data subsetted by specialty, physician specialty?
No.
If there are certain, would there be higher fraud rates in certain specialties than others?
No.
You know that?
What's the name of the drug you're talking?
Ritalin.
It's amphetamine. It's the same thing, same substance.
Amphetamine is here. You have amphetamine over there.
Oh, it's down there?
Yeah.
Okay.
It's a bit down the list, but it's there. So you have this idea that you can give a score to drug, and then if I have this score to drug and I weight that, so for a physician you prescribe a certain amount of drugs, you have a score for each drug, so you can take the average or weighted average of the drug score and give you a score. Problem is that you don't want your information of being a fraudster impacting the fact that impacting the drug score and impacting you back. So for each person, you calculate all the drug scores without him, and then back propagate all the drug information back to him. Right? So you can imagine that if you have 100 physicians, you have to create 100 times this simple graph and calculate everything. Turns out, because you can actually derive a closed formula of this total contribution, and just saying that the drug score is just the total drug score minus the contribution of one physician, you can actually write it very simply. And you don't have to iterate over 100 graphs. You can just calculate one thing and keeps just the one small contribution, and it's correct.
Do you see that once this information gets public, people change their patterns of creating? Like, if this is application from this in 2011 data,
of course, everything
how
changed.
applicable is it to 2013 data? Because it becomes public knowledge, and then you're completely, your features or whatever is not applicable to 2013.
Sure.
So
The first thing you do if you have this kind of model is that you predict your training sets and you try to find the fraudster which were not detected, because you must have some, right? I don't believe you detect every fraudster. So you probably can actually do a feedback loop first. So you look at your score and you look closer at I-scores. You decide if they're fraudster or not. And then you retrain your model based on this new target, which is a bit better. You do that several times in the year. Things probably haven't changed that much, at least not with your data. Then you can probably do better than, I don't know what's done today, but you can actually do some stuff. Now things are going to evolve, of course, but you need someone to actually create some smart features about this kind of fraud. That's why just using this supervised model is not perfect. You probably have to use some outlier detection techniques and so on as a complement. So that's something which is not normal. You see that and you decide if it's a fraud or not.
I still don't understand why it's not leaking. Because saying fraud and person fraud knows the information that you already know that it is fraud. I mean, to me, I feel like that's leaking when you calculate the score. Because you can't, when you calculate the score, you can't having this known information that it
From
is
the
already
test set.
fraud.
Yeah. I understand. So it's the same question as before.
Yes, but I didn't
yeah.
understand the.
So I think it's not really leaking because I'm not going to have another set, meaning I'm not trying to predict a hidden test set. I'm trying to predict my train set.
Okay, but then because in the training that's okay, you can calculate the score because everything is there. But the problem is like the same feature you need to apply to the testing data. But in the testing data, you don't have that information. So how could you calculate the feature? I mean, that's
for the test data, it's the same thing because.
So you're applying the testing data having the same pattern as the training data.
Yes, I know.
So you use the training data's kind of score and carry it over to the.
Yeah.
All right. Yeah. Well.
Yes, there is a leak. If you were to score other physicians which you don't actually know, but here since you have not a lot of frauds, there is some leakage, but I believe the model is still better than if you don't leak this information. So I understand. I agree. There is kind of a leak, but I'm not giving the information in the line. I'm more taking a global information from the distribution of the target in the test set, which I'm not supposed to know, and I put that into the training set, right? But I'm not using the target to actually create a line really deeply about the target. More using global stuff.
Depending on the holdout sample, do you do bootstrapping methods to keep on repeating the randomization?
Second.
Do you do any bootstrapping methods?
No, I used five-fold cross-validation. If that's what you mean. I'm not sure.
I'll have to check it, but I'm not familiar with that one. I mean, it's the ones like SAS, SPSS, we keep thinking random models.
Sorry?
Two different? Okay.
I'm not sure what you're talking about.
That's okay, I'll go check what's on the system.
You use Bootstrap when you do like random forest?
Yeah. Oh, not for random forest, no. Okay, this is not, that's for logistics, I'm sorry.
You can bootstrap the model, like bagging for the model, for creating the model or for evaluation?
For creating the training set.
It's okay to training set.
You re-extract the
Okay. Yeah, it's kind of similar to cross-validation.
It's similar to
cross-validation.
means
Yeah.
that you
Sure.
use to separate the
No, here I'm just showing cross-validation with 80% and 20%. I did fivefold, which is kind of, you can see that as bootstrapping, but you don't pick with replacement.
Oh, okay, thanks, okay.
Which is kind of, let's say, classical stuff overview. But Bootstrap is another possibility.
Thank you.
All right.
Very good, thank you.
We got 2 claps and something like that.
Great, right? All
Yeah.
great data out there.
Check for this event, we'll offer